Something is happening 15 billion miles away from you right now. A machine the size of a small car, built with 1970s technology, running on less electricity than a refrigerator bulb, is whispering secrets back to Earth, from a place no human eye has ever seen, a place no map has ever charted, a place where our sun's power simply ends and something else begins. And what it is finding out there is not what scientists expected. It is not what the textbooks predicted. And the closer Voyager 1 gets to silence, the louder the universe's hidden truth becomes. This is that story. Somewhere in the pitch-black void beyond the edge of our solar system, a machine is dying, not in a dramatic explosion, not in a Hollywood moment of fire and debris. It is dying the way old age takes everything, slowly, quietly, one system at a time. And yet, in the final chapter of its life, NASA's Voyager 1 spacecraft is sending back data so extraordinary, so deeply unsettling to our understanding of the cosmos, that scientists are struggling to explain what they are seeing. The question nobody in mainstream media is asking loudly enough is this: what exactly did Voyager find out there, in the dark between the stars? And why does it matter so much that it is still transmitting even as it fades? Voyager 1 is nearly 15 billion miles away from Earth, whispering back on a transmitter no more powerful than a refrigerator bulb. It is the most distant machine humanity has ever built. Think about what that means. The radio signal carrying its discoveries travels at the speed of light, the fastest thing in the known universe, and it still takes over 23 hours to reach us. By the time you finish reading this, Voyager's latest data will still be in transit, still crossing the vast, incomprehensible darkness of interstellar space, trying to reach home. And what that data contains is changing everything scientists thought they knew about the boundary between our solar system and the universe beyond. But here is where the story gets complicated. Because Voyager 1 was never supposed to be here. Not in this place, not still working, not still talking. Launched in September 1977, Voyager 1 was originally designed for a 4-year planetary tour. Jupiter, Saturn, a few years of data, then silence. That was the mission. Get close to the gas giants, take some photographs, gather some readings, and fade into history. But something happened that nobody planned for. The spacecraft kept working. The instruments kept functioning. The signal kept coming back. Year after year, decade after decade, Voyager 1 refused to stop. It became something the engineers who built it never imagined it would be. A messenger from the edge of everything, carrying humanity's curiosity into territory no probe had ever reached before. And now, nearly 50 years later, in the year 2026, it is sending back information that is making the scientific community quietly rethink the nature of the universe itself. Here is what most people are not seeing. This is not just a story about an old spacecraft running out of power. This is a story about what Voyager found when it crossed into interstellar space, what it is still finding, and why those findings are so profoundly strange that even the world's best astrophysicists are choosing their words carefully when they describe them. Both Voyager 1 and Voyager 2 detected a searing hot boundary zone at the edge of the Heliosphere, where temperatures spiked to an estimated 30,000 to 50,000 Kelvin. Read that again? 50,000 Kelvin. In a region of space that should, by most theoretical models, be cold and quiet, the Voyager probes encountered a wall of heat so intense that it defied expectation. The Heliopause, that transitional zone where the solar wind slows and collides with the interstellar medium, turned out to be a violent, turbulent frontier, not the gentle boundary scientists had imagined. It was the first major shock. It would not be the last, because what Voyager 1 encountered after crossing that wall was even stranger. In 2012, Voyager 1 crossed an unprecedented boundary and became the first human-made object to enter interstellar space. The moment it crossed the Heliopause, the invisible line where our sun's influence ends and true interstellar space begins, the data changed, the instruments registered, something the engineers had not fully anticipated. The space between the stars was not empty, it was not silent. It was filled with plasma, with magnetic fields, with turbulence, with a kind of cosmic weather that had nothing to do with our sun and everything to do with the ancient violence of stars that died millions of years before our solar system was born. Voyager 1 had not found emptiness. It had found a living, breathing medium, a hidden ocean of charged particles stretching endlessly between the stars. Measurements from Voyager's plasma wave system revealed density fluctuations that trace interstellar turbulence across regions spanning tens of astronomical units. And they found this without needing solar shocks to generate the signals. What that means in plain language is this. The interstellar medium was producing its own wave patterns, its own rhythms, entirely independent of our sun. The cosmos was talking, and Voyager was the only instrument in existence positioned to hear it. Scientists published findings showing that persistent plasma waves had been detected from 2017 onward, enabling a steadily sampled measurement of interstellar plasma density over a region no other operating spacecraft could reach. This was not a one-time anomaly. This was a continuous signal, a steady hum, a voice from the deep universe that had never been heard before, because no machine had ever been far enough to hear it. Think about what that means for our understanding of everything beyond our solar system. For decades, astronomers modeled interstellar space using theoretical calculations and distant observations from telescopes. They looked at stars. They measured light from billions of miles away. They built elegant equations and refined computer simulations. But they were always guessing in a sense because no instrument had ever actually been there, physically inside the interstellar medium, to take direct readings. Voyager 1 changed that. It did not just cross the boundary. It became a research station operating in the most inaccessible laboratory in the history of science. And the readings it was sending back were, in many cases, contradicting the models. The turbulence was stronger than predicted. The plasma density was behaving in ways that were unexpected. The magnetic field structure at the boundary was more complex than any simulation had captured. This is not chaos. This is discovery. But it is discovery that raises far more questions than it answers. According to informed sources at NASA's Jet Propulsion Laboratory, the data Voyager 1 has been transmitting from interstellar space represents something entirely unique in human history, a direct measurement of a region that every other telescope can only observe from a distance. If our Heliosphere is a ship sailing interstellar waters, Voyager 1 is a life raft just dropped from the deck, determined to survey the currents. And those currents are not what anyone expected. The interstellar medium is not a calm sea. It is a complex, turbulent environment shaped by forces that stretch across light years. Forces generated by stellar explosions, by cosmic magnetic fields, by the collective gravitational and energetic legacy of stars that lived and died before our sun had even formed. And here is what most people are not seeing. Every one of those discoveries was made possible by instruments that are now being shut down, one by one, as Voyager 1 approaches its final years. On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent commands to deactivate the low-energy charged particles experiment, one of the few remaining science instruments still operating aboard Voyager 1. The decision was not made lightly. The LECP instrument had been operating almost without interruption since Voyager 1 launched in 1977, nearly 49 years. It measured low-energy charged particles, including ions, electrons, and cosmic rays, originating from both our solar system and our galaxy. The data it gathered helped scientists understand the structure of interstellar space, the pressure fronts, the varying particle densities, the shock waves radiating outward from solar events and into the cosmic medium beyond. And now it is gone, switched off by a command that took 23 hours to arrive, because that is how far away Voyager 1 has traveled. As of April 2026, Voyager 1's radioisotope thermoelectric generators are producing less than half their original power output, declining by about 4 watts every year. 4 watts per year sounds small. But when you understand that the entire spacecraft is now operating on a power budget thinner than a household nightlight, 4 watts is the difference between 1 more year of science and silence. Engineers developed a step-by-step plan years earlier for shutting down systems in a specific order while preserving as much scientific capability as possible. Each Voyager originally carried 10 sets of instruments, and 7 have already been turned off. The LECP was the 8th to go on Voyager 1. And this is where the weight of what is happening truly lands, because only 2 instruments remain. As of April 17, 2026, only 2 Voyager 1 science instruments remain active, the magnetometer and the plasma wave subsystem. 2 instruments, 2 sensors. Out of the original 10 that launched with Voyager 1 in 1977, the magnetometer measures the local magnetic field, a critical reading in interstellar space where magnetic structures are still poorly understood. The plasma wave subsystem listens for electromagnetic signals in the surrounding medium, continuing to track the density and behavior of the interstellar plasma that Voyager first entered over a decade ago. These 2 instruments are, right now, the only human-made sensors operating in interstellar space. And as Voyager mission manager Kareem Badarudin put it, they are still working great, sending back data from a region of space no other human-made craft has ever explored. But let us step back for a moment, because the urgency of the power situation tells only part of this story. The real story, the part that should occupy every front page and every science headline on Earth, is about what Voyager's plasma wave instrument continues to detect, even now, in its final operational years. The Voyager 1 plasma wave system has given point estimates of plasma density spanning about 30 astronomical units of interstellar space, revealing a large-scale density gradient and compressive turbulence outside the Heliopause. 30 astronomical units of direct measurement from a single instrument on a dying spacecraft. To understand the significance of that number, consider that 1 astronomical unit is the distance from the Earth to the Sun, approximately 93 million miles. 30 of those units measured directly from inside interstellar space. No simulation, no distant observation, direct physical contact with the medium itself. The data coming back from Voyager's plasma wave system has revealed that the very local interstellar medium is structured in ways that challenge existing astrophysical models. Layers of density, pockets of turbulence, regions where the plasma behaves in ways that suggest influence from ancient stellar events, far beyond what our instruments could previously detect. Because the plasma waves Voyager detected were not generated by our Sun, that detail is critical, and it is what makes the discovery genuinely unprecedented. Previous studies of interstellar plasma density relied on the detection of plasma oscillation events triggered by shocks propagating outward from the Sun. In other words, before Voyager's latest findings, scientists could only measure interstellar space by watching how it reacted to our Sun. They needed a solar event, an eruption, a shock wave, to trigger the electrons in the interstellar medium into oscillation, and then they would measure that response. It was indirect. It was reactive. It was like trying to understand the depth of an ocean by throwing rocks in and listening to the splash. What Voyager found was different. The persistent plasma wave signal appeared to be not generated by solar activity, but may instead be related to an intrinsic process in the interstellar medium itself, possibly thermal density fluctuations in the quiescent plasma. The cosmos was vibrating on its own. The interstellar medium had its own rhythm, its own pulse, completely independent of anything our Sun was doing. And Voyager was detecting it. For the first time in human history, a machine was measuring the baseline heartbeat of the space between stars, not as it responded to our Sun, but as it simply existed in its natural state, undisturbed and ancient. The implications of that discovery are staggering, and the scientific community has only begun to process them. What most people are not seeing is that this changes the framework through which we understand our own place in the galaxy. For most of human history, we have thought of our solar system as a kind of island, a bubble of sunlight and warmth floating in the void. We understood that the void existed, but we had never truly touched it, never tasted it, never measured it from the inside. Voyager 1 did. And what it found is that the void is not empty. It is not featureless. It has structure. It has density gradients. It has turbulence that traces the large-scale forces shaping the galaxy itself. Voyager 1 and Voyager 2 have now reached heliocentric distances of approximately 172 and 143 astronomical units, respectively, and are approaching regions of maximum plasma and neutral atom density predicted at 200 to 250 astronomical units from the Sun. They are heading deeper into a structure that, according to the latest kinetic models, grows denser and more complex the further they travel. And they are doing it on failing power, with instruments switching off one by one, racing against time to send back as much data as they can before the lights go out. In November 2026, Voyager 1 will become the first spacecraft in history to reach a distance of 1 light day from Earth, approximately 16 billion miles. 1 light day. That is the distance a radio signal traveling at the speed of light covers in a full 24 hours. Think about what communication looks like at that distance. If a mission controller says, "Good morning, Voyager 1," at 8 a.m. on a Monday, they will receive Voyager's response at approximately 8 a.m. on Wednesday. 2 full days. 1 question, 1 answer, 48 hours of waiting. This is not a technical inconvenience. This is a fundamental reframing of what communication means when the machine you are talking to is on the edge of the observable human universe. And the engineers who are managing that conversation are working against an increasingly narrow window. An unexpected drop in power levels during a routine roll maneuver in late February 2026 brought Voyager 1 dangerously close to triggering its automatic fault protection, a self-preservation mode that would have shut down critical systems and required a risky, multi-day recovery process. Read that again. A routine maneuver, the kind that is performed regularly just to keep the spacecraft's antenna pointed at Earth, nearly triggered an emergency shutdown that would have taken days to recover from. Days during which no data, no signal, no contact would have been possible. The margin between functioning spacecraft and silent wreckage is, at this point, measured in watts. Literally. A few watts separate Voyager 1 from the moment it stops talking to us forever. According to informed sources, the team at JPL made the decision to shut down the LECP precisely because that power drop in February was a warning. It was the spacecraft telling its caretakers that the budget was running out faster than anticipated. Engineers expect that turning off the LECP will provide Voyager 1 with approximately 1 additional year of operation. 1 year. That is what the sacrifice of a 49-year-old instrument, one that survived planetary encounters with Jupiter and Saturn and more than a decade of interstellar travel, is worth in terms of extended life. 1 more year of data, one more year of plasma wave measurements, one more year of magnetic field readings from the only location in the cosmos where such readings are possible. The people managing this mission understand the weight of what they are doing. Voyager's team includes NASA retirees in their 80s who advise on specific subsystems, alongside team members so young that even their parents were not born when the probes lifted off. This is a mission that has outlasted careers, outlasted decades, outlasted every expectation that was set for it. The engineers who built Voyager 1's instruments are, in some cases, long retired. Some have passed away. The machine they created has outlived many of them, and it continues to send home discoveries they never imagined it would make. What most people are not seeing is how intimate this moment is. Voyager 1 is not just a scientific instrument. It is the furthest physical extension of human civilization that has ever existed. Every piece of it was touched by human hands. Every circuit was designed by a human mind. Every instrument was calibrated and tested and launched with human hope and human ambition. And now it is out there, in the dark between the stars, doing what it was built to do, even as it slowly runs out of the energy to keep going. And the discoveries it continues to make in these final years are not footnotes. They are not epilogue. They are the most significant readings in the spacecraft's history, because they are the only readings ever taken from where Voyager is right now. The magnetometer is measuring the local magnetic field in interstellar space. A critical reading because interstellar space is not empty, and the magnetic structures within it remain poorly understood. Scientists have long modeled the interstellar magnetic field from a distance, but the difference between a model and a direct measurement is the difference between a map and the territory. Voyager's magnetometer is giving scientists the territory, actual field strength readings, actual directional data, from inside a region that exists beyond every boundary our sun creates. And what those readings are showing is that the magnetic field in the very local interstellar medium is more structured, more ordered, and more dynamic than the models predicted. Meanwhile, the plasma wave subsystem continues to listen. And what it is hearing is a universe that is far more active, far more turbulent, and far more complex than the quiet void that astronomy textbooks have long described. The interstellar medium, according to Voyager's direct measurements, is not passive. It is alive with density waves, with electromagnetic oscillations, with the long echoing aftermath of stellar events that happened before Earth existed. Every measurement that comes back is a new data point in a map that has never been drawn before. Every signal that makes it through the 23-hour transit from the edge of the solar system to the deep space network antennas on Earth is a message from the universe's most unexplored territory. But here is the deeper truth that sits beneath all of this. The real story of Voyager 1 in 2026 is not just a story about science, it is a story about time running out. It is a story about what humanity chose to send into the void when it had the chance, and what that void has chosen to reveal in return. Sometime in the 2030s, if the spacecraft survives that long, NASA expects the power margin to shrink to the point where even the final science instrument can no longer be kept alive. The radio signal may persist briefly afterward, but the science mission will be over. The last measurement from interstellar space will be taken, the last data point will be transmitted, and then, in the decades that follow, Voyager 1 will continue sailing outward, silent, dark, but still moving, for billions of years, long after the Earth itself is unrecognizable. And here's what makes that future genuinely sobering. We have no plan to replace it. There's currently no mission approved, funded, and on a trajectory to reach interstellar space in the near future. The next generation of probes capable of crossing the Heliopause and entering the interstellar medium would require decades of travel time to get there. Meaning, even if a probe were launched today, it would not reach Voyager's current position for well over 20 years. The window that Voyager opened, the window of direct interstellar measurement, will close when its last instrument goes dark, and it will not reopen for a generation. That means every data point coming back right now is irreplaceable. Every reading from the plasma wave subsystem, every magnetic field measurement from the magnetometer, every whisper that travels 23 hours across the void to reach an antenna in the California desert or a tracking station in Madrid or Canberra. All of it irreplaceable. None of it can be recollected. Once Voyager falls silent, that particular view of the universe, from that location, at this moment in the solar cycle, from this specific position in the interstellar medium, disappears forever. And there is something else. Something that the mission team at JPL has noted in its most recent status updates that deserves far more attention than it is receiving. By the end of 2026, Voyager 1 will reach a new milestone, becoming the first human-made object to travel a full light day from our planet, a distance of approximately 25.9 billion kilometers. When that happens, on November 18th, 2026, to be precise, the signal delay will cross the 24-hour threshold. From that point forward, any command sent to Voyager 1 will not arrive until the following day, and any response will not return until the day after that. The spacecraft will, in a very real and practical sense, be operating beyond the reach of anything resembling real-time human control. Think about what that means for the final instruments. The plasma wave subsystem and the magnetometer will continue taking readings, storing data, and transmitting it back. But by the time any anomaly is noticed on Earth, it will already be more than a day old. By the time a response command is formulated and sent, another day will pass. The reaction time for any crisis aboard Voyager 1 is now measured in days, not hours, not minutes. The spacecraft is, in every meaningful sense, on its own. A 1970s machine, running on 49-year-old technology, operating alone in interstellar space with no possibility of rapid human intervention, still doing science. This is not chaos. This is the most extraordinary engineering achievement in the history of human spaceflight. And yet the achievements keep coming. Because even as Voyager's power fades, the data it is transmitting continues to challenge and expand our understanding of the cosmos. Voyager 1 continues to reveal in stark detail how interstellar plasma and the solar wind collide and interact across the Heliopause boundary layer, where they engage in a massive pressure balancing act that shields our heliosphere from the great beyond. That pressure balancing act, the constant push and pull between our sun's outward streaming solar wind and the inward pressure of the interstellar medium, is what creates the heliosphere that protects every living thing on Earth from the full force of galactic cosmic radiation. Understanding that boundary, understanding its structure and its dynamics is not just a matter of scientific curiosity. It has direct implications for understanding how habitable zones form around stars, how life is protected or exposed as planetary systems move through different regions of the galaxy, and what the long-term radiation environment of any world depends upon. Voyager 1 is answering questions that go far beyond the spacecraft itself. The real story is this. For nearly 50 years, humanity has had a probe in the most extreme environment reachable by any technology we have ever built. That probe has found a universe more dynamic, more structured, more surprising than our models predicted. It has found heat where there should have been cold. It has found persistent wave signals where there should have been silence. It has found complexity in the magnetic architecture of the space between stars that demands new theoretical frameworks to explain. And it has done all of this while slowly, systematically shutting down, piece by piece, instrument by instrument, until only two sensors remain to whisper the universe's final secrets back to Earth. The question that nobody is fully prepared to answer is what happens when those last two instruments go dark? What does it mean for human understanding of the cosmos when the only direct measurement station in interstellar space falls silent? What theories will we be left unable to test? What structures in the interstellar medium will we be unable to monitor? What changes in the heliosphere's boundary, changes that directly affect the radiation environment of our solar system, will go unmeasured because the one instrument capable of measuring them is no longer functioning? And perhaps most profoundly, what else is out there in the space between the stars that Voyager has not yet reached? The interstellar medium extends across the galaxy. Voyager has sampled a tiny sliver of it, a narrow corridor stretching from just beyond our heliopause to a distance of about 172 astronomical units from the Sun. But the nearest star, Proxima Centauri, is over 4 light-years away, more than 268,000 astronomical units. Scientists predict that Voyager is approaching regions of maximum plasma and neutral atom density at 200 to 250 astronomical units from the Sun. It will reach those regions as its power is failing, as its instruments are shutting down, potentially unable to fully characterize the very zone it was unknowingly heading toward all these decades. The universe has a timing problem, and the timing problem is not in our favor. What is coming is not just the end of a mission. It is the end of an era of direct interstellar measurement that humanity spent nearly 50 years unknowingly building. The engineers who designed Voyager 1 did not plan for it to become an interstellar probe. They did not plan for it to outlast the Cold War, the fall of the Soviet Union, the rise of the internet, the invention of the smartphone, and the arrival of artificial intelligence. They planned for 4 years and got 50. They planned for the outer planets and got the stars. They planned for a mission and created a monument. And right now, on the edge of the solar system, in the darkest and most distant place any human creation has ever reached, that monument is sending home its last great messages. 2 instruments, 1 magnetometer, 1 plasma wave detector. Against the void, against the dying of the light, still measuring, still transmitting, still, against all expectation and all precedent, doing science. What they find in the time that remains, and what it means for how we understand the universe beyond our cosmic doorstep, may not be known for years, perhaps decades, as scientists continue to analyze the data long after Voyager goes silent. But one thing is already certain. The universe out there is stranger, richer, and more alive with hidden structure than we ever imagined. Voyager 1 proved it. And the question it leaves behind, The question that will drive the next generation of interstellar exploration is not what we found. It is what we have not yet found. What is out there in the deeper interstellar medium, in the regions beyond Voyager's reach, in the space between the stars that no probe has ever touched? Nobody knows. And that, perhaps, is the most terrifying and most thrilling truth of all.